We'll continue talking about solutions today, and this will be the last component for your quiz. Previously, we talked about properties of solutions as well as examples. You now know how to express concentration many ways. You know how to do molarity, molality, mole fraction, and you know how to make a solution by dilution. And that's something we're going to be exploring in the lab. And that will help you really understand the dilution process as well as how to make solutions two ways. Today we're going to be looking at solution-based graphs, and in a second lab you will be generating a solubility curve. We'll introduce them today, but you'll be doing it in the lab either next week or when we get back. And also next week we'll be looking to calculate freezing points, boiling points of solutions, as well as the molar mass of a solute that has made up a solution. So there's a lot left to go in this chapter, and today we're really going to focus on graphical analysis. We're going to keep it very simple. Some of the graphs I've given you are quite complex, but we're going to keep it simple, and you'll be very successful with this section. There are a few terms we want to define here so that when we look at the graph, we'll know what we're looking at. First up, solubility. This is the amount of substance that's needed to make a saturated solution at a specified temperature. When a solution is saturated, it has dissolved as much solute as it can. For example, when a sponge is saturated, it's filled with water. If you squeeze out that sponge, then you will release some of the water and you will have an unsaturated condition. When you are saturated with knowledge, you just look at me and you're like, that's it, I can't stuff anything else in my head. Or when you're studying for a test, and if you're saturated at that point, it doesn't matter what extra you do, you're not going to stuff anything else in there. Same concept. And we know how to use our solubility rules, and that's something you'll be given your solubility rules on the quiz, and you'll have to apply them. So make sure you're comfortable using them. We've gone over that in class. We're going to categorize solutions either as saturated, unsaturated, or supersaturated. And as I said, saturated has dissolved as much solute as it can at a certain temperature. An unsaturated solution doesn't have as much solute as it can dissolve in it. And we can see that on the following video here. I'm just going to flip screens to make sure I have that up on the screen. And that's what you'll see here. There's no voice in this. A little tricky to read. I'll highlight the key points to you. So there's a beaker with water, and you've just thrown in a solute, and you can see it's disappearing down here. It's not really disappearing as much as it's dissolving. So initially all the solute is able to dissolve in the water, creating an unsaturated solution because the concentration of the solute is less than what it can be. And then as you add more and more solute, the concentration increases, but the solute will continue to dissolve until maximum solubility has been reached. And we'll talk about how to determine that using a solubility curve. So again, it's dissolving, and soon it's going to start to collect on the bottom because you're going to get to a point where you're saturated. You cannot dissolve more solute in solvent. And it says once the concentration exceeds the maximum solubility, additional solute added to the solution cannot dissolve and will accumulate on the bottom, and you'll have a supersaturated solution. And this is somewhat, can be a little confusing, this concept, but we'll take a look at it in a simpler fashion. And this is actually very cool. A supersaturated solution contains more solute than a saturated solution can normally hold. And typically what you've done here is you've dissolved solute in solvent, you've heated it up. If you add a seed crystal, and you'll see that in just a sec, the crystals are going to precipitate out and you get this whole cascading display. And you see this with your very sugary foods, for example, rock candy, which I'm sure you've had at carnivals, etc. This is a super saturated solution of sucrose in water. There are other examples as well. You can actually do a demo with this with sodium acetate, and that's what you're going to see here.
Okay. Just really quick, I'm going to add one tiny sea crystal. I'm not sure you can see on the tip of that.
So right here you have a solution of sodium acetate, and here's the seed crystal right here. If you were doing something with sucrose like rock candy, you might throw in a sugar cube.
Sweet with that. At the tip, I'm going to add that to my super saturated solution of sodium acetate.
And watch right here.
And we will see it go from a super saturated state to a saturated state in just a few seconds. Isn't that cool? So we see that the sodium and acetate ions recognize the crystalline structure of that seed crystal I just added. And then add to it. And we form one big crystal. And one egg-shell crystal inside, you can see. It looks like a big chunk of this, doesn't it? So now we're back, there's a little bit of water in there, you might be able to see it. We're back to our saturated state right now. So we've gone from super saturated to saturated in just a couple seconds. All right, you like that? Lovely. Just really.
And again, your real sugary foods, the honeys, jellies, things like that, all from a super saturated state that then crystallizes or precipitates out. There are two factors that affect solubility. One is temperature, the other is pressure. And we're going to take a look at solubility of solids dissolved in liquids. That's typically the type of solution you make, but we're also going to take a look at gases dissolved in liquids. And what you typically see when you have a solid dissolved in a liquid is the solubility will increase with an increase in temperature. And this is one of the reasons why when you wash your hands, and nowadays we tend to use liquid soap, but back in the old days we all had bars of soap, and you probably use a bar of soap in the shower. And unless that water is warm, you're not going to get the soap to go into solution. So what we're going to do in this case is we're going to take a look at the effect of temperature on solubility. And I want to take a look at it a couple of different ways. And I want to keep it very simple initially so that you can understand it. We're going to be looking at solubility curves. And you'll get a taste of it today, but you're actually going to be generating solubility curves in a secondary lab next week. And this is kind of fun because most of you have never seen snow, and so you'll have the opportunity to see snow in a test tube. What you're really seeing are crystals. But with solubility curves, we first want to look at a solid dissolved in a liquid, and then we're going to take a look at a gas dissolved in a liquid, and we want to look specifically at the effect of alteration in temperature on solubility. So if we look first at a solid dissolved in a liquid, what we're going to see with its solubility curve, so I'm going to make a graph, and what I've got on the X is temperature, and this can be in degrees Celsius. So let's say I have 20, 40, 60, 80, 100. And on this axis, so I'm going to push this over now, you have solubility. And this is going to be the mass of solute in grams over 100 grams of water. So that's your mass of solvent, but it's going to be per 100 grams of water. Maybe I should do this. And let's do 10, 20, 30, 40, 50, 60, 70. I'm going to label this on the inside just so it's easier to read. Typically, you know, you do it on the outside. And I'm going to generate a curve such as that one. So this would be some solute dissolved in 100 grams of water. So clearly it'd have to be water soluble. Below the line, you have your unsaturated region. On the line, you have your saturated region. And above the line, you have your supersaturated region. And what you can see there is as you increase the temperature, the solubility of the solute in water increases. And that's what most solids show when dissolved in a liquid. As you increase temperature, the solubility will increase and you can dissolve more and more solute in the water to a certain extent. So if we're looking at the effect of temperature on solubility of a solid dissolved in a liquid, as we increase the temperature, what happens to the solubility? It increases. Okay, now let's consider a few questions here. Let's say the first question is, at 20 degrees Celsius, what mass of solute dissolves in 100 grams of water to generate a saturated solution? So I look at 20 and I'm going to see where I hit the line, because I know on the line is saturated, and now I'm going to trace back, and it looks like that's about 18 grams of solute per 100 grams of water. So again, the temperature, go to the line because that's saturation, trace to the left, and that's the approximate mass of solute per 100 grams of water. Now, if I had asked you at that temperature what mass of solute dissolves in 200 grams of water, what would the answer be? 36. And if I said what mass of solute dissolves in 50 grams of water at 20 degrees Celsius, you would have indicated 9 grams. So there's some cutesy little ways you can ask questions there. Just be careful. Now let's say in a second question, I state that at 80 degrees Celsius, 20 grams of solute dissolves in 100 grams of water. Is the solution unsaturated, saturated, or supersaturated? So how would we do that? We'd look at 80 and the intersection of 20, which is right here, and that would fall in what region? Unsaturated. I'll go ahead and put I'm at a slight angle, I hope it's lining up well. So that would in fact be unsaturated. So as you increase the temperature, the solubility of most solids dissolved in liquids increases. Questions here? And we're going to be doing quite a bit more of this when we do the lab, but there's a classwork section on this, part 2, that will help you. I want to do a little bit more analysis in your notes. There is a solubility curve shown in your notes right here. Which substance of those listed is covalent? Sugar is a covalent compound, typically compounds that start with carbon R, but in addition, you can see here that you have all nonmetals. Thank you. So sugar is a covalent compound, all the others are ionic. What else do you see on the graph that jumps out at you? The red mark. So you've got these reddish pinkish lines. And what are the red lines showing? They're going down. So with an increase in temperature, the solubility of those solutes is doing what? Decreasing. And what do these two substances on the red lines have in common? They're both sulfates. So sulfate containing compounds don't show this increased solubility with increase in temperature. Otherwise, you can see here as you increase temperature, you increase the solubility of potassium chloride, potassium bromide, sodium nitrate, and potassium nitrate. Potassium nitrate shows the greatest solubility range with temperature, and we do use potassium nitrate in the lab because it's much easier to find or record the temperatures at which crystallization takes place to generate the solubility curve, but we'll take a look at that. Now let's also focus for a sec. Let's pick these three just because they're in a line. We have potassium bromide, sodium bromide, and sodium nitrate. Which of those three substances generates a saturated solution at 80 degrees Celsius because it shows 150 grams of solute dissolved in 100 grams of water? That would be the sodium nitrate because you're right here. So again, if you just follow the intersections there, you'll generate your point and you can interpret it.
How do you know where the saturated, unsaturated, and supersaturated are on that one?
For which substance?
Like just for
Any of them?
Yeah.
If you have potassium nitrate right here, this is its line. Okay? So above that line would be supersaturated. So at 40 degrees Celsius, if you had 180 grams of potassium nitrate and 100 grams of water, you'd be right where my cursor is, and you'd be supersaturated because it's above the line. It's like Super means above. A superscript is high up. Superlatives.
So like, if you would give a question about the 40 degrees and then like 180 grams, you could say which one is not super saturated and be sugar.
Sure.
Okay.
That'd be sneaky though. That'd be harder than I'd make it. I'll let you write the test. And then for sodium nitrate, so this line right here, what mass of sodium nitrate would exhibit a saturated solution in 100 grams of water at 20 degrees Celsius? So right around 85 maybe. So if you had 200 grams of water, what mass would dissolve? Without a calculator? How about? Okay. What did I say, 300 or 200? At 200? Yeah, that's fine. And we'll get a lot more practice reading solubility curves because you'll be generating these in the lab and then interpreting them. Not difficult to do. Very easy type of question you might see. You could see it on the test in a multiple choice format even. Very straightforward. Now in contrast, whereas the solids dissolve in liquids show an increase in solubility in most cases with an increase in temperature, that's not what you see with the gas dissolved in a liquid. So if we go over here and we've got solubility versus temperature, that's not a good pen. And again, your solubility, I'm going to turn it sideways just so it fits. And this particular unit's a little bit different. It's 10 to the negative 3 molar. But what you see with gases dissolved in liquids is the reciprocal effect. So as you increase the temperature, you decrease gas solubility. You see that with soda. You get your soda out of the fridge, you open it, you drink it, and you leave it out, flat. Because the gas comes out of solution at the higher temperature. You do not increase the temperature of your fish tank too much. What's going to happen to the dissolved oxygen? It's going to come out of solution and your fishies are going to go belly up and, you know, all drains lead to the ocean. So do not increase the temperature on your fish tank. You go to the beach, which we do a lot down here. Are you going to find the fishies swimming right on top of the water there at the surface or way down low? Way down low. Where is the water colder? Way down low. Where's there going to be more dissolved oxygen? Down low. Same thing. All right? So gases dissolved in liquids show this reciprocal type of effect. As you increase temperature, you decrease the solubility. So one factor that affects solubility is temperature. Now for gases dissolved in liquids, another factor that affects solubility is pressure. And you see this too. Many of you unfortunately drink soda. Not so good for your bellies or certainly not your teeth. But pressure also affects gas solubility. But gas solubility increases with increasing pressure, and this is why soda is canned under very high pressure conditions. You open up that soda can and you essentially relieve the pressure, if you will, and you'll see the bubbles rising up to the top and they will pop as the bubble gets larger and larger. What's the relationship between pressure and volume? Inverse or direct? Inverse according to whose law? Boyle's law. Good, good, good. And this is what happens in soda. When you reduce the pressure, the dissolved gas leaves the solution as small bubbles. As they rise, they increase in size. They're encountering less pressure. Again, the inverse relationship between pressure and volume. And when they reach the surface, they're going to burst. When you close it, there's an equilibrium. But again, when you open it, you're going to have issues. Two factors that affect solubility: temperature and pressure. If you were given a solubility curve, you would want to know how to read it as much as I've shown you here, and you'll see it in your classwork as well. The next thing I want to show you is strictly for extra credit. Those of you moving on to AP next year to play for another year, this will help you in a certain section that the kids find to be very, very challenging. We're going to keep this very simple. In the other honors classes, if they've asked you for help, they probably learned about net ionic equations when they balanced equations, and you were like, oh, we didn't learn that. I don't teach it there because you don't know your solubility rules yet, so you don't know what is and isn't water soluble. So how can you write a net ionic equation? So we're going to do it here. We're going to keep it really simple. You'll see it on the quiz in the form of extra credit. You'll see it on the test in the form of extra credit. Really easy. Good chance to just cash in a little bit more. With ionic equations and precipitation reactions, sometimes when two solutions, and that's two aqueous solutions, maybe let's throw that in. When two aqueous solutions are mixed, I put it in right there, an insoluble material called a precipitate will form. A precipitate is a solid. You have generated precipitates in the lab already, and you'll be doing more of it in the fourth 9 weeks. Certain double replacement reactions will generate a precipitate. A precipitate is a substance that doesn't dissolve in water. It's insoluble. It is a solid. The molecular equation you would be able to write if I told you silver nitrate and potassium chloride, both of which are aqueous, react, you would be able to generate those products because this is a double replacement reaction and you were all very strong at predicting products. However, it is more appropriate to write this equation as a net ionic equation rather than as a molecular equation. First of all, you have ionic compounds, metal, non-metal. And I'll walk through this long way of doing it, and then I'll show you a shortcut that I feel you'll be very successful with. So one of the earliest chapters in AP is chemical reactions, and it's always extremely challenging because there's so many different types and it's not as easy as what we did in honors. But in this one, your molecular equation, which I am abbreviating ME, I'm just rewriting it. You already have it in your notes, no reason to rewrite it. Silver nitrate reacts with potassium chloride. Both of these are aqueous, which means they're water soluble. And I told you it generated silver chloride, but you'd be able to put the outsides and insides together. Silver chloride is not water soluble. There are certain chloride containing compounds that are not. There are 3 of them, and it's in Rule 3 as we talked about previously. And your other product is potassium nitrate. One way to go about getting a net ionic equation is to first write an ionic equation. And basically here, anything that's aqueous, you're going to break up into ions. Silver ion, nitrate ion, potassium ion, chloride ion. So the same way you formula write, you unformula write. You never bust up a solid. For those of you into this, you're going to want to write it down. Do not break up a solid because you will crash and burn. And then potassium ion and nitrate ion. This is aqueous. In a double replacement reaction, one product will be a solid and the other will be aqueous. And if I didn't tell you potassium nitrate was aqueous, how would you know that anyway? All nitrate ion containing compounds are water soluble, and all group 1 ion containing compounds are water soluble. So you could hit Rule 1 or Rule 2 here. Okay, this is an ionic equation. You have ions or you have a solid that isn't soluble, so it's not going to bust up into ions. A net ionic equation has just the ions and the solid that is made from those ions in the equation. So in the ionic equation, you would cancel any ions on both sides of the equation. Bye-bye potassium ion, bye-bye nitrate ion. Potassium ion and nitrate ion are spectator ions. They are not directly involved in the generation of the precipitate. They are spectator ions. It's like going to a basketball game and watching it. The spectators are not on the floor playing hoops. They're just watching it. Now they can influence the game because we all know there's a home field advantage, but they do not physically get down on the court and play unless they've gone nuts, and then they'll get arrested. So your net ionic equation is what you have left. Silver ion plus chloride ion makes silver chloride. And that is a net ionic equation. Now, is there an easier way to go from the molecular to the net ionic? There sure is. So let's give it a shot. What I would have done with this first one is I would have looked at my two reactants. And when I look at reactant 1, I've got silver nitrate, and I know that all nitrate ion-containing compounds are water-soluble. So I wouldn't go after the nitrate ion. I'd go after the silver ion. Now, if I have a cation here, am I going to react it with another cation or an anion? Anion. So I know from this compound, I had to be going after the chloride ion. In addition, I'd never go after a group 1 ion. And from this alone, I can get my net ionic equation. And we'll try it a few different times. If I were asked for my spectator ions, my spectator ions would be potassium ion and nitrate ion. Does it look hard? It's really not. Alrighty. There's a whole gobbledygook written down in your notes for you, just as a backup plan, but we'll walk through a few examples. And I didn't put any in your classwork, but certainly if you want more, I'm sure I could come up with 10. And you can work through them with minimal difficulty. Again, I've listed everything down that I told you. There's an example shown here in longhand. Let's try and do it in shorthand. It says to write a net ionic equation for the reaction that occurs when aqueous solutions of lead-2 nitrate and ammonium iodide are mixed. Identify the spectator ions. Okay. So the way that I would approach it at your level is I have lead-2 nitrate. Now if you can't formula right, you're in big trouble. And ammonium iodide. Based on what we've discussed previously, which ion, the lead-2 ion or the nitrate ion, do you think we must go after to write a net ionic equation?
Not the nitrate.
Not the nitrate ion, so definitely the lead-2 ion. Now I've got a cation here, so what do I need from here? Anion. In addition, all ammonium ion containing compounds are water soluble. And what product would we make? Lead-2 iodide, right? Is that balanced? Is it balanced now? And if I asked you for the spectator ions, they're the ones we didn't use. nitrate ion, and ammonium ion. And you've just earned yourself extra credit. Let's try another one. It says barium chloride reacts with sodium sulfate. Now you might not be sure what you're going after in the first reactant because it's not going to be obvious to you right away. But if you look at the second reactant, what ion must you be going after? Never a group 1 ion. Never, ever, ever a group 1 ion. So you have to be going after the sulfate anion. So if you have a sulfate anion, what are you going to grab from here? The barium ion. And what do you make? Now that's your solid, the one that doesn't dissolve. What are the spectator ions? Chloride ion and sodium ion. Because those would make table salt, and we know you can put table salt in water.
Wait, if you took the precipitate out, would it like form salt?
This is a
With
salt.
Yeah, but then with like sodium and chloride, would those form a salt?
If you were able to solubilize this, you would not generate a solid because all the substances you would make are both water soluble. We're going to talk about phase changes, and this is going to lead into colligative properties that we get into in our next lesson. There are a tremendous number of definitions in your notes here, but I really want to keep it very simple for you. You've seen phase changes since elementary school, but let's diagram it in a fashion that will be very comprehensible to you and very easy to study from. So in regard to phase changes, we're going to be considering 3 states of matter. We've got solid, liquid, and gas. And when a substance transitions from the solid to the liquid state, that phase change is known as melting, transitioning from liquid to gas, that is known as
Evaporation.
vaporizing or boiling, boiling must occur at constant temperature and pressure. Evaporation doesn't have to. Gas to liquid would be condensing, and from liquid to solid would be freezing. You can go from solid directly to gas, that is known as subliming. And we'll take a look at sublimation. And you also can go from gas directly to solid, and that is deposition or deposing, how snowflakes are formed.
Wait, the top one is sub what?
Subliming. bless you. And we can look at sublimation. Iodine, under standard conditions, exists as a solid. So shown in the left panel, you've got those crystals at the bottom of the Erlenmeyer flask. It is capped, and some of the iodine in the solid state has undergone sublimation, hence that purplish color on the flask all throughout up above. Here you can see the solid state where the molecules are vibrating in a fixed position, and there the gaseous state where those diatomic molecules are bebopping around very rapidly, far less particle arrangement. Sublimation directly from solid to gaseous state. You see this also, for example, with the plug-in air fresheners. You've got solid and directly to the gaseous state. There are several definitions here. I want to mention vapor. When we talk about hydrogen gas, for example, we indicate that it's a gas, but iodine that's undergone sublimation, while it may be in the gaseous state, we tend to refer to it as iodine vapor because it doesn't commonly exist in the gaseous state. So when a substance more commonly exists as a solid or a liquid and it's in the gaseous state, we refer to it as vapor. We know that gases move in a straight line fashion and exert pressure on the walls of the container, and this is known as vapor pressure, the partial pressure of the vapor above the liquid. This is based on intermolecular forces. You'll go into that in a college level class, nothing that we need to talk about here. Substances are highly volatile. They easily transition from the liquid to the gaseous state. And for example, ammonia, you open up the bottle and you're like, ooh, that really smells. Some of the hydrochloric acid we've used this year is highly volatile. It readily moves from one state to another, and these are volatile substances. Somebody who has a volatile personality will go nuts over the smallest thing, and so they go from here to here very, very quickly. Same type of situation. Boiling, we know, occurs when a substance transitions from the liquid to the gaseous state. It occurs at both constant pressure and temperature. That does not need to be the case for evaporation. The boiling point of a substance, abbreviated commonly as TB, is the temperature at which the substance changes from liquid to gas. When those two states coexist and the temperature is constant, you have the boiling point. It's something you could do in the lab. You could heat up water and measure the temperature, and when the temperature remains constant over time, you've got your boiling point. You'd see the vigorous bubbling. You can define boiling point in terms of vapor pressure. You'll see that the boiling point is the temperature at which the vapor pressure of the liquid equals the external pressure acting on it, and at 1 atmosphere, water will boil at 100 degrees Celsius. You can apply the same type of analysis to freezing. Freezing point, again, is the temperature at which the substance changes from liquid to a solid, and at 1 atmosphere of pressure, you can determine the freezing point of a substance such as water. The reverse of freezing is melting, as we mentioned previously, and sublimation we talked about as well. One of the easiest ways to represent 3 states of matter is through a phase diagram. Shown here is a phase diagram for water, and we're going to look at the relationship among the temperature, the pressure, and the physical state. So we've got pressure on the Y and temperature on the X, and we're going to look at all 3 states of matter. Before we get into this diagram, I want to look at something a little bit simpler. I think this will help in terms of understanding. Again, pressure on the Y, temperature on the X. You've got 3 regions here. Green is solid, blue is liquid, and yellow is gas. As you transition from solid to liquid, melting point, so solid and liquid will coexist along this line here. and depending on what the standard pressure is going to be, you can determine the melting point. Along this line is where liquid and gas coexist. They are at a state of equilibrium. We'll talk more about equilibrium later in the year. And then if you go directly from green to yellow, you've got sublimation. A is the point where all three phases exist. All three phases are at equilibrium, and we'll see this at the molecular level. And point B in this curve is the critical point. Here you still have liquid and gas. Above this point you have what's known as a supercritical fluid. You cannot have both states of matter anymore. At the molecular level, if we look at this for carbon dioxide, we've got solid. You can see the molecules vibrating in a fixed position. Liquid, less particle arrangement, more movement. Gas, far less particle arrangement, far more movement. Intermolecular forces have been broken. At the triple point, and that's why at the molecular level it's kind of cool, you can see all three states of matter coexisting. Solid to liquid, you can see those two states coexisting. Liquid to gas, you can see those two states coexisting. Here's the critical point, above which you'll have a supercritical fluid. So if I said to you, you're transitioning from solid to liquid, you're going across here, you would indicate that that's melting or boiling. That would be melting.
I was gonna ask, what would be an example of a real supercritical fluid?
Oh no, look it up. Good question. What'd you get?
I have to log in because I didn't.
This particular curve shows it for water. There's a funky thing here. You've got a negative slope right here. That's because water is weird in that it expands when it freezes, and as a result you'll see this negative slope here. But otherwise you have solid, liquid, and vapor. Solid to liquid, so this will be the transition line. Here's your melting point at 1 atmosphere of pressure, 101.3 kPa. Water melts at 0. Here's your liquid to vapor transition. So again, at 1 atmosphere of pressure, boiling point is 100 degrees Celsius. Here's your triple point. All three substances coexist. Here's your critical point. In regard to the critical point, you can see this visually. So this is 10 degrees below the critical point, and you can see liquid and gas. And now as you get closer and closer to the critical point, that line is blurred and the particles are behaving far more similarly. And then at the critical point, you have a supercritical fluid. What do you got, Juliana?
Nitrogen, like in a pressurized container.
Is it supercritical fluid?
I guess so. I mean, I'm still looking.
You know, we do use liquid nitrogen in the lab to freeze things, but I just thought it was in the liquid state. I didn't realize it was supercritical.
That's how they like make ice cream.
Mm-mm.
Yeah, liquid nitrogen, they put it on there. Supercritical carbon dioxide can be used instead of perchloroethylene for dry cleaning. It just
What do you got, Dylan?
I just have a question.
Okay.
What about like dry ice? Like what's that? Is that like what does dry ice do? Like what would it be like?
Dry ice is actually carbon dioxide in the solid state.
So what happens when you melt it? Can you melt it?
It just sublimes, I think. Goes directly from solid to gas.
They use supercritical water as a medium in which to oxidize hazardous waste. Supercritical water gasification is a process of exploiting the beneficial effect of supercritical water to convert aqueous biomass streams into clean water.
I don't know. I'm gonna ask Miss Dublin. Maybe she knows. Alrighty.
Oh, in fridges.
In fridges,
Yes, supercritical carbon dioxide. It's a refrigerator.
it's a refrigerant.
Yeah.
Cool. See, it affects everybody sitting here because you're all gonna get into that fridge later.
What fridge?
You're gonna eat later, aren't you?
Maybe, but maybe.
Alrighty. In any event, if I told you, I'll show you how easy a quiz question might be.
Do it.
If I told you you were in the blue region, what state of matter do you have?
Liquid.
Alright, and if I said, what is point A, you would tell me it's the triple point. That's how easy it'll be. I promise. Alright, last thing for the day before we get into the lab. And this, I don't know, I know my daughter saw it in middle school. I don't know if you did. This is a heating curve for water, and this is something we used to do in the lab, but the kids told me it was so incredibly boring that I cut the lab from the curriculum. So here's water in the solid state. Here's solid water and liquid water coexisting right here. So is that going to represent melting or boiling?
Melting.
Melting. So where you have a plateau, that's going to represent a change in state. So that's melting at 0 degrees Celsius. Here's water in the liquid state. Here's liquid water and gaseous water coexisting. So that represents what phase change?
Boiling.
Boiling. And is the temperature constant?
Yes.
Yes. And here's steam, water in the gaseous state. Why does a burn from steam cause far more damage than a burn from boiling water?
Particles are moving
Because
faster.
it's hotter. Look, the temperature's higher. So it's going to cause a more severe burn. And yes, the particles would be moving faster at that temperature. So here's a heating curve for water. And I give you such a curve on your classwork, and you'll get some additional practice with this. In terms of the graphical analysis we've done today, we took a look at solubility curves. And on classwork 3.3s, you'll find more problems like the ones we did in part 2. We also talked about phase diagrams. And you'll see more questions about phase diagrams on the classwork. This will be part 3. And then finally, take a look at heating curves, and you'll be asked to draw a cooling curve, just the mirror image of a heating curve. And this will be in part 4. So for next time, you want to finish up this classwork. And in regard to your quiz, which will be during our next class period, what you'll see on this quiz, you'll see solubility rules. You'll see concentration questions of molarity, molality, mole fraction, and dilution. And you're going to be working with dilution in the lab as well. And then finally, you'll have one graph-based question from something we looked at today. And that'll be your whole quiz.
Daylight savings is on Sunday.
Questions here? All right? We introduced boiling and freezing very briefly today because we're going to be getting into colligative properties next time. But at this point, you want to make sure you have mastery of these concepts listed here.